This tutorial is one part of three where we're going to discuss mixture modeling. Specifically, we're going to look at Gaussian mixture modeling. And the main idea with this type of mixture modeling is we are assuming that the data that we have is actually generated by a number of hidden or underlying distributions. And the point of doing this is we're trying to understand or hypothesize exactly what those distributions are. So this can be done with data that has a single feature. It can be done with data that have many features. It's much easier to visualize, certainly with one or two features, than it is with many. In the first step, we're going to do a couple of things. We're going to import some libraries from PySpark. In this case, we're using Gaussian mixture and Gaussian mixture model. In the second command, we are defining the file path that links to GMM data. This GMM data is provided by Spark, and so while in the next two tutorials we'll look at some real data, in this case this is generated by Spark for demonstration purposes. Be sure that you change the file path to correspond to where the data is located on your own computer. We're going to create an object, an RDD, called GMM data using the SC text file approach. And when you read this in, if you want to double check that the data is read in, make sure that you're getting something similar to what I have here. So in the first step, we're going to, so you can see the data below, we need to tell Spark that this data is actually in floating point format. So right now it's difficult for it to parse. So we're going to do this using a map function. We're going to create an object called formatted data, and it's going to be this GMM data. We're going to call a map function on this. This lambda function, if you recall, is an anonymous function. And within this, what we're going to do is we're going to say for each line, we are going to strip each element of that line, and we're going to split by space here. So notice that this split is called on space. That's corresponds to how our data is delimited. So that means if we were looking at a CSV file where we have commas, this would certainly be done differently. But again, the purpose of this line is so that we are dealing with floating point numbers, and that is what these Gaussian mixture model expect in terms of formatting. So if we look at formatted data and we look at perhaps the top 5 or so we're breaking back in after a brief pause of making a mistake, something that is probably useful to think about. Initially we had this piece of code where we just said float x for in line.strip. The problem is that it does not know then exactly what x is. So we need this for loop in here in order to define it. So if we then look at this particular data, we can see that we have floating point numbers now, which is what we wanted to have. So we are then going to we're going to create an object, GMM model, and that's going to be created by calling the Gaussian mixture train on the formatted data that we created above. And this 2 is a parameter. So when you are defining a Gaussian mixture model, you have the option of defining how many underlying distributions you'll hypothesize there are. In some cases you might think, have a reason to believe that there are a specific number, so this 2 is a parameter value. It's not necessarily something you have to use every time. But if we create this GMM model object, you can see it will take a little while to process. So the question is, how do we look at things in this object? So it's not something where we're going to look at training. We're not going to be able to look at test and training and how accurate the model was at doing predictions, because we don't have labels here. This is an unsupervised task. So what we're going to do is we need to be able to look at the distributions, right? The whole point of this mixture model is that we find these underlying normal distributions. So it makes sense that we would want to look at the parameters that we have. So we're going to create a loop that looks through these two parameters, we're going to print weight. So this will just make sure that when you are actually looking at this, it comes out in a more interpretable way. So in the first part, we're going to say weight is equal to GMM model.weights. So .weights is something you can call from the object. It will return a weight amount for each of the distributions that you generated. We'll also do this for the mean. And again, we can take our GMM model object and we can call Gaussians on this. And so this is, again, what this is doing is it is saying from this model, call the underlying distributions that I have, and then for that particular model, give me the mean. And lastly, we also need an amount of variance, right? Every model, when we're talking about a normal distribution, comes with two parameters, mean and variance. And so just like before, we're going to call Gaussians again, and in this case, we're going to call it on I, right? And so this I is corresponding to looping through. So the whole point here is that you're iterating through the two distributions that you returned from the process. And with the sigma, we are going to return this to an array to make it easier to read. So if we actually go through and print this, let's see if we did it right. Well, it looks reasonable. So what we see here is we have a weight for each one. We have a dense vector for mu, and we have an array for sigma. So while it's certainly beyond the scope of what we'll discuss here today, these are the parameter values. So you were able to get back these parameter values and recall that your original data had two features present, which is why we see there's not just a single number for the mean, it is actually a vector, and in the case of variance or sigma, it is actually an array.